So we are recording the video this week because we have a teacher-directed day right on top of when I am too normally scheduled for the week. So this is for days 10 through 14, LP7. So just as always, make sure that you're going through and working on Alex to get your homework done. All homework this week will need to be done on Alex. We're obviously not going to have math class, so we're not going to be doing any of the worksheets like we have been in class. So make sure you're logging in, working on that homework. It's worth that 50% of your grade, so it's definitely very important. Topics, tests, and quizzes are smaller chunks of your grade, but they are definitely chunks of your grade. So you want to make sure that you're working on each one of those. Just make sure, log in on a daily basis and get your homework done there. The more you work on it, the easier it will become because you're getting used to working with those types of formulas and equations or concepts. The shorter amount of time we spend on it, if we try to do everything all at once, we don't really learn a whole lot from things like that. So we want to make sure that we're working on it on a regular basis to kind of train our brain to think that way. So just make sure, log in, work on Alex. Everything is due on Sunday, just like normal. And yes, extensions are available. Make sure, reach out if you need help. We have tons of resources. Yes, you can ask me. I'm your math teacher, so of course, please ask me. We have in-center tutoring. We have the FEV 24-hour, 7-day-a-week tutoring that you can do online. That's through clever.com. I did hear that you have to download some kind of Google extension so that they can share screens, but doesn't sound like a super horrible or crazy step. I made YouTube videos for every single one of the homework assignments on top of this video. And then you can ask, you can look at questions, examples, and explanations, and even videos right in Alex that they made. So lots and lots of resources there. So make sure, use your resources. Okay, so let's go ahead and get started here. So this is day 11. We're going to look at angles of elevation and depression. So first, we're just going to review the sine, cosine, tangent ratios. These are the trigonometric ratios we learned last week. So up here we have so, and it's going to go so katoa. If you remember from last week, it just fills in. It's a silly, little way to remember the trigonometric functions. So I color-coded this to make it a little easier to decipher here. So SOH is so. So S stands for sine, and sine of an angle is the ratio of the opposite side over the hypotenuse. And we'll go through and label this. So if I go like this, here's the angle we're focusing on is angle A. We could also focus on angle B. You never focus on angle C because it's the 90-degree angle. You always are looking at one of the two acute angles. So we're going to look at A. We're going to say, okay, well, let's look at the opposite side of A. So that's what we label opposite. And then if we look at the 90-degree and we go to the opposite side of that, that's always the hypotenuse. And this is true no matter what. If we go to the 90-degree and across, that is our C, or our hypotenuse. The angle that we're looking at determines the actual opposite side, the one we call opposite. So if I'm looking at A, opposite would be the little a. If I was looking at angle B, the opposite would actually be the little b, or this green side. So just be, aware, pay attention to which side you're looking at. So I just put the letters over A over C, and I'm even color coding it. Here's red, here's blue. And then we have Ca, so C-A-H. So C stands for cosine, and the ratio for cosine is the adjacent side over the hypotenuse. So adjacent just means if I've labeled this opposite and this hypotenuse, I only have one side left. That's my adjacent side. And we can think of that's the side that creates the angle. So the hypotenuse and the other side that creates the angle. That's the adjacent side. It's the other side there. So that's B, which we can see I put B up here, and then C, because that's still the hypotenuse. And the last one is TOA, or for tangent. So again, this is just a cute little way to remember these trigonometric functions. So katoa. So we have T for tangent, and the ratio for tangent is the opposite side over the adjacent side. So we've already labeled this. Opposite side was A, adjacent side was B. And just like I kind of already said, it depends on which angle we're looking at. That'll change the opposite and the adjacent. So it says down here, would the ratios be the same if you were looking at angle B? Well, if I was looking at angle B, this would not be the opposite of angle B because I want to go to the opposite side, which would make this guy the adjacent. It's the other leg or other ray that created this angle B. So if I'm looking at the other angle, it would actually switch. It would change the opposite and the adjacent, not the hypotenuse. The hypotenuse doesn't move or doesn't change because it's still across from that 90. So the only thing that happens if I switch angles is opposite and adjacent kind of switch places. All right, so let's go ahead and practice this guy. So first, I like to label hypotenuse, opposite side and adjacent side. So if I'm looking at a 16-foot ladder and it's leaning against this house here, the angle of elevation of the ladder is 67 degrees. How high is the top of the ladder from the ground? So they want to know, where does this point land? How high is that? So if we look at this for hypotenuse, that's going to be across from the 90. So it's usually the easiest one to label real quick is just saying, here's my 90, I'm going to go across from that. And then if we look at the angle and we go opposite the angle, that is my opposite side. So if you do hypotenuse and opposite, then adjacent is the other side there. And again, remember, it's going to be hypotenuse and adjacent make the angle you're looking at. So I can see the blue and the green. Those are the two rays that make the 67-degree angle. So we have a hypotenuse and an opposite side. We need to identify which ones do we actually have so that we know which trigonometric function to use. So we're going to use sine. So the sine of an angle is equal to the opposite side over the hypotenuse. So now let's fill these in because we actually have some of these amounts. So instead of just an angle or theta, we're going to put 67 degrees. I used question mark because that was what was on the diagram. And then 16 for hypotenuse. And to bring this back just a second for the question mark, you can use anything you want for a variable. It truly doesn't matter as long as you're not using a number, because you don't want to use a number. And you want to be careful with certain letters, like I say don't use O because it could look like a 0, something like that. But you can use anything you want. I've used the question mark before, I've used the @ symbol, I've used smiley faces. It's just a placeholder. Keep that in mind. So question mark's perfectly fine. All right, so what we want to do, I want to get this 16 out from underneath the fraction here because I want to know what just question mark is. So I'm going to multiply both sides by 16. Now I need my calculator. There are tables in the textbooks that will help you do, sine of an angle, but we can do this on a calculator pretty easily. So, oopsie, that should say multiplication. I don't know why that switched to division. That was silly. So we're multiplying by 16, not dividing. So we're going to go in here and we're going to type in 67. That's my degree. And then I'm going to come down here and I'm going to click the sine button. And it's going to give me this nice long decimal. So this is actually that ratio, like opposite over hypotenuse. If I divided the two numbers for those lengths, it would give me this number here, this decimal. So it's that same ratio. It'll divide it for you. It knows what to do. So if you're looking at a textbook, there are tables, but it will only give it to you, I think it's either 4 or 5 decimal places out. It doesn't give you the whole thing. So now we're going to multiply by 16. So that gives us this nice big number, and we're going to round that off. We're not going to write this whole thing. I think we're going to round to a 10th. So remember, if we're rounding to a 10th, you want to look at the next number here. That's a 2, which is 4 or smaller. So everything's just going to kind of delete off of there. We're just going to have 14.7. So we can see it here, 14.7. They didn't give us units. Oh, they did say feet here. They just didn't put it here. So I should have written 14.7 feet because that's how high up the house it's going. All right. So with this one, this is just a cute little diagram to show you what angles of elevation versus angles of depression mean. And I know it sounds funny to say angles of depression, but we just want to think of elevation as going up, depression is going down. So with this one, this is an angle of depression. If this person is up here on top of the the Eiffel Tower, then they are looking down, right? They're going to look down to the ground. So they have an angle of depression. This person down here at the bottom is looking up at the Eiffel Tower. So this is an angle of elevation. Okay. These two angles will be the same when you have angles of depression and elevation. Sometimes they're going to give us an angle at the top, and we need to bring it down to the bottom. Or sometimes they give us the one at the bottom and we need to bring it to the top. The reason they're congruent, and this is going back to when we were practicing parallel lines and transversals, is we're pretending like this person is looking straight off, or we're kind of making a parallel line from the top of their head or their eyes. We're doing the same thing from this person. So this is a straight line from her eyes. Not that she's looking straight, just it's a straight line, a parallel line with her. So the top and the bottom are parallel, and this line of sight is a transversal because it crosses the two parallel lines. So this angle at the top and this angle at the bottom are what we call alternate interior angles. They're on alternate sides of this transversal, and they're in between or inside the parallel lines that we just created. So they're alternate interior angles. So this is just kind of a cute little reminder. When it says angle of depression or angle of elevation, this is all it means. Okay, so let's take a look at the word problem that goes kind of with this one. A ramp 18 feet long rises to a platform. The bottom of the platform is 11 feet from the foot of the ramp. Find x, the angle of elevation of the ramp. So x is the angle that they want us to find, and they want us to round to the nearest tenth of a degree. So don't round until the very end. Be very careful about intermediate rounding, or rounding within the computations there, just because that can throw off the answer by a tenth or more, and then depending on how picky Alex is being about it, it could very well mark you wrong because you rounded too early. So just be careful about that. Try to leave everything in your calculator as far as the decimals go until the very, very end. All right, so let's go through and we're going to label this guy. So we have an angle of elevation, right, for this ramp. So x is my angle of elevation, and then I'm going to label hypotenuse. Here's an adjacent side. So I didn't label the opposite side because I don't need it. It doesn't give me any information about it. If it helps you to label hypotenuse and then opposite so that you know this is the kind of extra angle, or not angle, sorry, extra side, then that's perfectly fine. But because I'm using hypotenuse and adjacent, that's cosine. So I definitely want to remember those trigonomic functions from that very first slide because they're going to kind of keep coming up here. And the more I kind of have those memorized, the easier this is. Now, can you have your notes pages in front of you? Do I expect you to have those in front of you? Of course I do. I want you to have those with you so that you can reference them as you're going. All right, so we're going to take the cosine of an angle, and that's going to be the adjacent over the hypotenuse. So let's fill these in. So we don't know the angle, so I just left it theta. That's a Greek symbol for angle. But I do know the adjacent side is 11 and the hypotenuse is 18. So now I can go over here and go 11 divided by 18. Sorry, I kind of did that quick, but divided by 18 equals, and here's a decimal again. To go back to the angle, this is a little bit of a different step when you're looking for the angle. You don't want to just go down here and hit sine or cosine or tangent. You want to hit second, and then you'll see it changes. I have this little inverse, this -1. And this is what I want to press when I'm looking for the angle. So now I'm going to press the inverse of cosine. And here's the angle, 52.33. And I'm only going to 10th, so I'm going to round it off to that 3 because the next one is 4 or smaller. So it's 52.3 degrees. That's my angle of elevation here. All right. So now we're going to look at solving a triangle with the law of cosines. So remember, the trigonomic functions, sine, cosine, and tangent, require a right angle, those ones that we did at the beginning. There are two laws that can be used when no right angle is present. We have the laws of cosine and the laws of, the laws of sine and the laws of cosine. So first, we're going to look at the laws of sine, okay? Because we're actually going to look at both in the same section, but we're going to focus on this guy first. So remember, this means we have some kind of triangle like this where there's no right angle, and don't assume, even if something looks kind of sort of like a right angle, we don't assume that. We go with what the diagram tells us. I'm not being told there's any right angles, so there are no right angles. So with this one, we have these three ratios. we can go the side A over the sine of the opposite angle, which is going to be the capital letter for it. So it's going to be the sine of angle A. Or I have the side B over the sine of angle B, because it's opposite that side, and then C over the sine of C. So, and the C was cut off down here, but there's a capital C right here. So we're only going to be using two of these at any one time. It kind of depends on the information they gave us. So we know they're all equal to each other, but depending on the information they give us in the problem, I'm only going to be using two of them at a time. I'm not going to use all three. So let's go ahead and take a look at the problem they give us here. So it says, consider the triangle ABC, like the one below. Suppose that angle A equals 61 degrees, B is 55 degrees, and side A equals 6. Keep in mind, capitals are angles, lowercase are sides, always when they're doing this. The figure is not drawn to scale, and they want you to solve the triangle. When they tell you that the figure is not drawn to scale, they're literally telling you do not measure anything. They don't want you to take a ruler out. They don't want you to use a protractor to measure angles. You want to solve this mathematically, not by measuring. The diagram is just more to kind of visually represent it. So solve the triangle. When we say solve the triangle, what does that mean? Well, it means find all the missing pieces. They gave us 3 pieces. Well, there's 3 angles and 3 sides. So I'm missing 3 pieces there. I'm missing 2 sides and 1 angle. They also want us to round our answers to the nearest tenth. If there's more than one solution, use the button labeled OR. So far, I have not found one that gives me 2 answers, but it is possible, especially when we're taking square roots, although I'll show you what I mean when I get there with this one, because square roots, you don't want positive and negative, because these are measurements. They're not going to be negative. So I think that would be the only time that you would come up with 2 answers with the OR, is if you had a positive and negative answer, but we would get rid of the negative one because that's called an extraneous solution, meaning it doesn't make sense for our situation. So we're going to go through and label some of these. So here's 61 for angle A, there's 55 for angle B, and side A is 6. So we do need to remember a couple of theorems as we go here. Triangle sum theorem, or the triangle angle sum theorem, tells us that the 3 angles of a triangle add up to 180 degrees. Well, they gave me 2 angles, didn't they? So I can very easily say 61 plus 55 plus angle C, which is the only one they didn't give me, have to equal 180 degrees because they are a triangle. So if I combine these, I get 116 plus C equals 180, and I'm going to subtract 116 from both sides. So angle C is 64 degrees. So I already have one of my pieces filled in. I need my other 2 though. So now we're going to determine which 2 ratios we can use based on the given information. So if I look at this guy, oh, that didn't animate quite right. There we go. So I have A over sine A and B over sine B. And I chose that because I have angle A, I have side A, I have angle B. I want to know what angle side B is. Sorry, I have angle B, but I want to know what side B is. So that means I have, of these 4 pieces, I have 3 of them. So that's how you determine which ratios to use. You need 3 of the 4 pieces in order to fill this in. So this shows me I only have 1 variable left over when I fill this all in. So I have 6, because that's side A. Angle A is 61, so I'm going to take the sine of 61, and that's going to equal side B, which I don't have, divided by the sine of 55, because that's angle B. So now I'm going to cross multiply, because we have 2 ratios that equal each other. That's called a proportion. As soon as we have 2 fractions equaling each other, we cross multiply. So I have 6 times the sine of 55 equals sine of 61 times B. So remember, cross multiplication is just a very fast way to get rid of the fractions. That's what it's for. All right, so now I'm going to divide by sine of 61 on both sides because I want to get B by itself. And I'm doing this all before I even look at the calculator because these are going to give me very long, not repeating decimals, but non-terminating decimals. So I don't want to clear them out once I start typing this in. So I kind of want to do this all in one step on the calculator. So here we're going to go to the calculator now, and we're going to say 6 times 55, and then I'm going to click sine. So with this one, I have to type in the angle first and then click sine. I think on Alex, you have to click sine and then 55. So be aware, different calculators may respond a little differently to how you type things in. So this is the sine of 55. When I hit times again, I think I actually skipped over that. Oh, that might have been it. I don't think I'm actually showing you the full piece here. Because when I hit times, this was the two pieces together. So now we're going to divide by 61. The sine of 61. Sorry, I have to hit sine again. And we're going to get this number. I need to make sure I hit equals. Otherwise, it was just showing me that that's the sine of 61. That's not the answer. I need to make sure I hit equals one more time so that it actually tells me what the answer is. So it's 5.6. I want to round that to the nearest tenth. So it's going to be 5.6. So, and again, just be aware with the calculator, different rules go into the calculator and how you do this. So I literally started with 6 and then went times the sine of 55. So 6 times 55 and then click sine. And then it shouldn't be times again, it should be divide, but that's okay. Divided by 61 sine. And then again, that is the sine of 61. I need to make sure I hit equals so that it finishes the calculation there. Because it's going to show you kind of intermediate calculations. If you're doing this on Alex or on, I know there's some calculators online that kind of show you the whole calculation. Sometimes that's a little easier because you can actually see everything you've typed in instead of it refreshing every time you type a new calculation in. All right, so we have one more missing piece. We need side C. So now, and it's kind of animating funny here. So now I'm going to look at A over sine of A. I still have those two, but instead of looking at B, I'm going to look at C and sine of C. I didn't know what angle C is because we solved that with the angle sum theorem, but I don't know what side C is. I need to find that. So here it is, filled in again. It's 6 over sine of 61, C over sine of 64. So that's definitely different because it's a different angle. I'm not using 55 anymore. Now I'm using 61. Sorry, 64. Jeez Louise. So we're going to cross multiply again, just like we did in that first one. So we have 6 and sine of 64. And then we have sine of 61 times C. Again, I'm going to divide by sine of 61 on both sides because I want to get C all by itself. So we're going back to the calculator. We're going to have 6 times 64 sine. So there it is. And then we're going to divide by the sine of 61. So I'm going to click the button. And that's the sine of 61. Make sure you click equals so that you actually get the end calculation there. So we have 6.16. I need to make sure I round that up to 2 because 6.1 would be incorrect. Alex would mark you wrong for that because you did not round correctly. So be careful about that. You want to go 6.2, not 6.1. Pay attention to that rounding. All right, so this was law of sines. I think we are going to do one more with law of sines, and then we're going to look at law of cosines. So a pilot is flying over the ocean. She determines that the angles of depression to two ships are 64 degrees, so that's to ship B, and then 53 degrees, so that's to ship A. As shown in the figure below, the ships are 5 miles apart, so we know how far apart the ships are. Find the distance from the plane to the ship at point A. So we want to know what this dotted line is here, from the plane to A. So we're not solving the entire triangle, we're solving one part. And we're going to round our answer to the nearest tenth of a mile again. So I go through and I'm going to label A, B, and C. I'm also looking at angles of depression and angles of elevation. Because remember, this 53 degree angle of depression is this same angle of elevation at the bottom because they're parallel lines at the top and the bottom. And this dotted line that we want to find is our transversal. So these are alternate interior angles. Same thing with the 64 here. So I have 64 and 64. So we want to find this green line, it's a very bright green line that I put there. And we have angle B, and we are asked to find side B. So I have angle B, and we're asked to find this green line, which is side B. Remember, across is going to be the lowercase letter. That's the side. So the lowercase b is always across from angle B. The lowercase a, which would be side A, would be across from angle A. And then the lowercase c would be across from C. They didn't even label the plane C in this case, though. So we have side C, and we need angle C. So there's a couple of different things that we need to find really quick, because we have some information. I know this angle. I want to know this length, or this distance. I know angle A, but I don't know side A. I can find C, just like we're doing here with the triangle angle sum theorem. I can fill in angle C because I know what side C is, right? Even though this isn't labeled C, we always go ABC when we're talking about the law of sines. So if I go through and do the math here, I'm going to add the two angles together that I have, and then I'm going to subtract 117 from both sides so that I know 63 degrees is what's left over for angle C here. This has to be 63 degrees. So I could have looked at the line here. Angles on a line have to add up to 180 degrees, or the angles of a triangle have to add up to 180 degrees. Either way, it's the same calculation. So now I know angle C, I know side C, I know angle B, I want to know side B. I want to know side B. So I have 3 of the 4 pieces. I can set up a proportion, just like this. So again, notice you're only using 2 of the ratios. I think that's the most confusing part with law of sines, is there's 3 ratios to start with, and you have to choose 2 of them. And you always want to choose 2 that you can fill in at 3 of the 4 pieces. If you can fill in all 4 pieces, there's no need to set up that ratio. You already have all the pieces. It's not going to be solving for anything. So you want at least 1 variable there. If you have more than 1 variable, again, you can't solve it for that 1 variable. You're going to only be able to solve an expression of it with a variable in it. All right, so I'm going to scooch this guy up so we can do our cross multiplication. So we have 5 times the sine of 64 and the sine of 63 degrees times b. And I'm going to divide both sides by the sine of 63 so that I can get b all by itself, because these guys are going to cancel. All right, back to our calculator. So we have 5 times, and that wasn't supposed to pop up quite yet, times the sine of 64. Now it's supposed to pop up. And there it is. Now we're going to divide by the sine of 63. And remember, that is the sine of 63, so I need to hit equals. So there we go. It is 5 miles, and since that's a 0 and a 4, it's going to just be 5 miles. So the distance from boat A, or point A, to the plane is 5 miles away. It's by chance the same miles away that boat A is from boat B. All right, now we're going to look at the law of sines as far as proving it. So let's look at why the law of sines works. So we have the side lengths for a triangle ABC below are A, B, and C. So kind of the same idea we've had. We have A, B, C for the angles. Across from angle A here, this whole side is A, side A, lowercase. Across from angle B is lowercase b, if we go all the way to the other side. And then across from C, angle C, is that lowercase c. We're kind of ignoring that when I'm saying going across. We're going right through the height there. So the height of triangle ABC is h, and we call that the height because it's perpendicular to the base. In order for it to be a height, it has to be perpendicular to the side that we're calling the base in this case, and it can be any of the 3 sides. By chance, this one is side A, and it needs to go through a vertex in order to be called a height. All right, so fill in the blanks using the lengths A, B, C, and H to derive the law of sines. Make sure to use the appropriate uppercase or lowercase letters. And I'm going to assume when you go through and do this on Alex, it's going to be very similar to this example. I don't think there's too many variations of this guy. So we're going to use trigonometry to fill in the blanks. The only thing that might change is the angles that you're looking at, because we're going to look at 2 very specific parts, And you could switch those parts up a little bit, what you're focusing on. So this is a hypotenuse. If I'm looking at this angle here for B, I'm going to divide this visually into one kind of large triangle here, this right triangle, and this is across from the 90. That's my hypotenuse. And since I'm looking at angle B and I'm doing the sine, I want the opposite, which is H, over the hypotenuse. So I have H over C. Now I'm going to look at the sine of C. So I'm going to flip over and look at this angle, and I'm going to do the same thing. So now the hypotenuse is over here. It's B because this is also a 90. So I'm looking across. There's my hypotenuse. And angle C, if I go across from angle C, I still have H for my opposite side. But now my hypotenuse is B because I'm looking at a different triangle. So we're going to solve for H. That's what they want us to do from part 1 to part 2. So sometimes these prove the laws aren't necessarily my favorite as far as the steps go because it's not always clear exactly where they want us to go with the next step. But with this one, I can see they have H equals, so they want us to solve for H. So to solve this first one for H, I need to multiply by C on both sides. So if I multiply by C on this side, it's going to eliminate itself. C divided by C cancels. So I would just have the sine of B times C like I see here. On this one, I need to multiply by B on both sides. So, that's a typo. That should say B, shouldn't it? Because I was multiplying by B on both sides. So that was just an oopsie on my part. Make sure that you don't write down C, write down B. And now to go from part 2 to part 3, we're going to use some substitution here. If they both equal H, then I can substitute and say, well, if they both equal the same thing, they must equal each other. So I have C and C. Okay, that's going to bug me. I'm going to fix that. I don't like that. That should say B. And that should say B. Okay, let's go back through there. So that was just an oopsie. There we go. So it should say B and B. And hopefully I might have to go back and fix the bottom here also because it looks like I kept that mistake trickling through the whole problem here. So we're going to rewrite the equation from part 3. Basically, they want us to rewrite it as proportions. So we're uncross multiplying. So I'm going to divide both sides by C. I'm going to divide both sides by B. If I divide this side by C, they'll cancel, and it just kind of ends back up over here. So it'll be the sine of C divided by C. And then I can divide both sides by B. It'll cancel on this side, and it goes underneath. So this is a little different than the way we were looking at it on that first screen. Oh. Nope, that one was C, sorry. This one is the one I want to change to B. Uh-oh. I went forward to the wrong one. So they're upside down from the way we were looking at it on the first screen because I had the side over the sine of the angle. It's okay if you do the sine of the angle over the side, as long as you kind of keep that ratio the same throughout the whole problem once you decide. So sine of the angle, they're both on top. Side, they're both on the bottom. Or you can flip it and have the sides on the top and the angles on the bottom. It's not going to change the outcome because when we solve this, we cross multiply. So I'm still cross multiplying the same two things, whether they're on the top or the bottom. I just can't flip flop. So I couldn't put sine of B over B equals, and I couldn't have side C over sine of C. Like I can't flip flop it like that. I need to make sure angles are both in the same spot and sides are both in the same. So once I make that decision, I just have to stick with it. In this example, we used B and C for our angles for the law of sines. We could have used A and B. We could have also used A and C. So that might be how it's different when you're doing it. It's kind of luck of the draw there. It's one of the 3 options. So if yours is a little different when you're completing this on Alex, you'll probably complete it for one of the other 2 sides. So just make sure you're paying attention to opposite and hypotenuse of those angles when you're looking at it. All right, we're going to look at solving a triangle with the law of cosines. And let's look at the difference of why you would use law of sines versus law of cosines. So the law of sines is used when we're given either two angles in one side, three out of the four pieces, or two sides in a non-included angle. So it's kind of the reasons why you'd use law of sines. But with law of cosines, we're either given all three sides, no angles, just all three sides, or two sides and an included angle. So you just kind of have to know, if you're trying to set up the law of sines, the ratios tend to be a little easier to set up once you get used to using them than the law of cosines here, when we're going to look at them down at the bottom. But when you're looking at it, if you can't fill in three of the four pieces on law of sines, that's when we're probably going to move to law of cosines. They're always going to give you three pieces. It just depends on which three pieces they give you. But they are always going to give you enough to at least get started there. So with this one, we have these three equations. And we're only ever going to use one of those equations to solve a piece that's missing. So it kind of just depends on kind of the angle, actually. The angle is a big determining factor. So if you're given all three sides, then you're deciding which equation to use based on which angle I want to solve for. If you're given two sides and one angle, the angle will still decide which one you're using. Because if I'm given angle A, I have to use this first equation. If I'm given angle B, I have to use the second one. If I'm given angle C, I have to use the third one. And if you notice, there's kind of a pattern here. So I have a squared equals b squared plus c squared, which, we have our Pythagorean theorem a little bit there. This is actually Pythagorean theorem down here. A squared plus b squared equals c squared. But we have those three pieces. And so it equals a squared, and cosine of a is on the end. So it starts with a and it ends with a. And then I have b squared and c squared in here, and then I have minus b and c. So I have bc, bc. If I start with b, the side b, I'm ending with the angle b. And then I have a and c being squared, a and c being multiplied here by 2 and the cosine of that angle. If I start with side c, then I'm ending with angle c, and then I have a and b here being squared, minus 2 times ab. So there is a pattern here that kind of will help you remember how to write these. You just need to make sure that you kind of see the pattern, or definitely just have your notes pages open there so that you can see that formula, which one you're going to use. Because yes, there are three different equations possibly that we will use. All right, so let's go ahead and look at the question down below. It says, consider a triangle ABC like the one below. Suppose that A is 69 degrees and B is 35 and C is 6. Remember, lowercase means side, uppercase means angle. The figure is not drawn to scale again. Solve the triangle. So remember, solve the triangle means we need to find all the pieces we're not given. So first, let's go through and label this guy. So we have angle A, we have side B, and then we have side C. So there's my three pieces I was given. And I'm going to fill these in. So remember, it means find all the missing pieces. Well, I can fill in 3 of these 6 pieces here. There's 3 angles, there's 3 sides. I have 3 of those pieces out of the 6. And so now we're going to determine which of the 3 equations will work with the given information. So I'm given B, C, and A. Well, since we don't have 3 sides, we're going to look at the angle to decide which equation to use. I'm given angle A, I have to use this first one because it's the only one that references angle A. So we have to use this guy here because angle A helps us decide. And I've color-coded this so that it matches, exactly the way I color-coded it on here. So I have B is blue, C is green, and anything to do with A is red. And that's either angle or side. I just made them all kind of the same color. So let's go ahead and fill this guy in. Oh, that went too far. Interesting. That jumped a little far, but we have A squared. I don't know what A is, but I do know B is 35. I do know C is 6. And then this minus 2, remember that's part of the equation. That's going to always be minus 2 right there. Times B times C times the cosine of the angle that helped us determine we were using this, which is angle A. We know that's 69 degrees. So now I went down here and I already started calculating some of this. So 35 squared is 1,225. 6 squared is 36. 2 times 35 times 6 is 420 minus, because it was negative 2, times the cosine of 69. So I tend to wait off on actually doing calculations that I know will give me decimals until I'm ready to do the whole thing. So I'm ready at this point. I would type it in 1,225 plus 36 minus 420 times 69 cosine. So that's when I'm doing this on my smart calculator or my computer calculator. If you're doing it on Alex, I believe you have to hit cosine and then 69 or whatever degree it is. So just be aware of the different types of calculators there. So this is a squared equals 1,110 and 49 hundredths. I want to take the square root of both sides. I don't want to know what a squared is. I want to take the square root. So make sure you take the square root of it. So now I know a equals 33.3. You know, it just keeps on going and going. They're only concerned with a tenth. So the answer for a is 33.3. I'm going to keep this nice long decimal in here for my next step because I don't want to use the rounded version because that may round some of my other answers. Now I need to find angle B or angle C. Well, now I have enough to set up a proportion. I can even see that here. I have side A and angle A. I have side B. I don't have angle B. Or I have side C, but I don't have angle C. So I could set up that law of sines proportion with either one. It doesn't matter which one I do first because I need to find both. So I'm just going to start with B. And for whatever reason, I like the sides to be on the top of the fraction and the angles on the bottom of the fraction. Remember, it doesn't necessarily matter if it was flipped over because you're still going to cross multiply the same as long as they're either both sides are on top or both sides are on bottom. Both angles are on the bottom or both angles are on the top. You want to make sure that you always have the similar type of measurement in the same place. All right, so I'm filling in side A, that's that nice long decimal we just found, over the sine of 69 degrees. Side B is 6, and sine of B, I don't know what angle B is. That's my missing piece, right? So now I'm going to... What happened? Interesting. All of a sudden I flipped over to C. That was weird. So it flipped over to C, and I'm not sure why I decided to do that mid-formula there. But that's okay. It doesn't matter which one I calculate because I have to find both. So we'll do side C first for whatever reason. So I have this nice long decimal, this 33.3 times sine of C, angle C, and that's going to equal sine of 69 degrees times 6. I'm going to divide both sides by my 33.3 because I want to get sine of C all by itself. So I went through and I did this without showing it to you on the calculator, but I would go through and I'd type in 69 and then hit sine times 6. Sometimes I even hit equals in between here just so that it doesn't think I'm trying to divide just 6 by the next piece. So I would hit equals and then divided by 33.3, and I would go at least 3 or 4 decimal places out so that you have it. You don't necessarily need to have all of this, but I wouldn't just do 33.3 because it might round this guy a little too much. So we also need to go second and then sine for this one because I don't know the angle. So I don't want to just hit sine of the answer I get here. And I'm going to go ahead and grab the calculator because I think that might be a little less confusing. If I go through and I go 6, let me make sure I have the right numbers here. 6 times 69 sine equals divided by, so here I'm going to write this down really quick so you can see what it looks like on the calculator again. 329394. So divided by 33.329394724 sides should be a 3, but that's all right. I believe it would have been rounded. So I'm going to go ahead and hit equals. So this is the decimal. This is not the answer that I have on that screen, right? I need to hit second and then sine because I'm finding the angle. So this is going to give me the inverse of that ratio. So that's where that 9.7 comes from. So make sure you follow that last step. I should have had that on the slides there, but for whatever reason I was kind of going a little faster at this point instead of showing you the calculator over and over again. All right, so that's that angle C. Now I can use the triangle angle sum theorem to find that last angle. Once I have two angles, I know that the two angles, or the three angles added together, have to be 180 degrees. So I'm going to add those two angles together and then subtract so that I see what is left over for angle B. It's 101.3 degrees. So we use the law of cosines, we use the law of sines, and then we use the triangle angle sum theorem. So we use a lot of pieces here, kind of all together. All right, we're going to look at the law of cosines on a word problem. So we have an airplane leaves city A and flies 144 kilometers due north to city B. It then turns through an angle of 54 degrees and flies 97 kilometers to city C. So we can see they've actually labeled this for us, right? Flew 144, turned at a 54 degree angle, and flew 97 degrees. Sorry, 97 kilometers. And they want to know what was the angle with respect to due north. Could the pilot have flown to fly directly from city A to city C? So basically they want to know what angle, if I just started at city A and flew straight here, what angle would I have corrected by? Okay. So carry your intermediate computations to at least 4 decimal places. Round your answer to the nearest 10th of degree. So this is actually telling you, do not round within the problem. Wait until you get to the very end to round. That's what intermediate computations are. So you can already kind of see, this wasn't supposed to highlight quite yet, but we want to label our diagram. So we have A across from city A, B is across from city B, and C is across from city B. We can also fill this guy in. So before that goes, because we don't have any angles within the triangle, but I can fill this one in. We have a line here. So this is going to equal 180 degrees because they're supplementary angles. They're on a line. So I know 54 plus angle B, if I'm looking at the big angle here, have to be 180 degrees. So I'm just going to subtract 54 from both sides. So that tells me that this angle in here is 126 degrees. So now I have angle B, I don't have side B, I have side C, but I don't have angle C. I want to find out what angle A is, but I do know what side A is. So we need to start going through and figuring out these pieces here. So we use the equation with angle B. That's the only angle we have, and I don't have all 3 sides. I'm missing one side here. But we want to figure out what that one side is so that we can go back and use it to find this missing angle, because we don't have enough information yet to just go right in and attack angle A. So we have B squared equals A squared plus C squared minus 2AC times the cosine of B. And we are using this second equation. If we go back to that notes page, this was the second one because of that angle B. I know angle B. That tells me which one I have to use. So I don't know what B is, but I do know A is 97, C is 144, so I fill in my pieces here. And I do know angle B is 126. We calculated that right here. So now I'm going to go through and I'm going to square my numbers. I'm going to reduce this guy just a little bit, 2 times 97 times 144. So now I can type this all into a calculator. I'm just going to type this in, add them together, and go minus 27,936 times, I have to type in 126 and then click cosine. So I'm going to get this nice big number, 46,565 and 37 hundredths if I round. And I'm keeping at least 4 decimal places, like it told me. I want to take the square root. I don't want to know what B squared is. I want to know what B is. So I'm going to take the square root of both sides. So B is 215.79 hundredths, and I went out 5 decimal places on this one for whatever reason. I kept that extra 0. So now I know what side B is. So I know angle B, I know side B, I know side A, I don't know angle A. But if I'm thinking of law of sines, now I can use 2 of the ratios. I have 3 of the 4 pieces. So I can use A over sine A, B over sine B, and fill these guys in. So I know it's 97. I don't know angle A, but I do know side B, and I do know angle B. So I think the most difficult part of law of sines and law of cosines is making those decisions. There are just a lot of options. Because there's 3 options for law of sines, there's 3 options for law of cosines. So just knowing which one to use can be that hard part, deciding which law to go with. So we just want to kind of, if we list the pieces, sometimes that makes it a little nicer to see, like I had on that other sheet where you could see side A over angle A, side B over angle B, side C over angle C. When we had that on the other worksheet, that made it a little easier, especially for law of cosines, to eliminate or to pick the ratios we wanted. So let's do our cross multiplication here. So here we have our 2 pieces. We're going to divide both sides by that 215. So make sure when you're going through, you're going to go 97 times 126 sine, hit equals, then divide by 215 and 79 hundredths. And make sure you type this whole piece in, because this 0, 1 does make a difference. So when you type this in, we get 0.363662, and that equals the sine of the angle. This is when we want to hit second, and then that inverse sign, so that we actually have the angle given to us. We don't want this decimal. I don't want to know what the ratio is. I want to know what the actual degree is. So it's 21.3 degrees. Is this little angle down here. All right, I do believe we are going to prove the law of cosines. So let's look at why the law of sines works. This should say cosines. So that was a typo one again on my piece here, because we're looking at why the law of cosines work. So we're going to use Pythagorean Theorem to find a squared. So it's telling us that we're going to look at a squared. So we have another triangle very similar to that one when we were doing law of sines. We have A, B, C, we have side A, side B, side C, and we have a height going through here of H that's perpendicular to one side, and it's going through a vertice. So now if I'm looking at A squared, I'm looking at this kind of bigger right triangle here, the one on the bottom. So Pythagorean Theorem says A squared plus B squared equals C squared. Now that's a little off on this one, because remember A squared and B squared are the legs that create the 90, and C squared is the hypotenuse. So we want to make sure that we're identifying the hypotenuse. That's what A is here. It's across from this 90. So that's, if we're thinking of the original A squared plus B squared equals C squared, this is actually my C in that original equation. The letters are just getting a little jumbled here because we're moving things around. So we have our hypotenuse, and I have B, and I have A. This green and the blue line, that's the 2 sides that create the 90-degree angle. That's my A and my B. Those are my legs. So that's my A squared and my B squared. So I have x squared plus h squared equals a squared. So that's why I bubbled in this guy here. Now we're going to use Pythagorean Theorem again to find c squared. So now I'm looking at c squared. I'm looking at the little tiny right triangle over here. So now I have c is my hypotenuse, so that's normal. And then I have this little blue piece here, which I'm filling in. I know the entire side is b, and this side is x. So I need to go the whole side minus this x. So I have b minus x. And then I have this other leg here, which is h. So I have h squared plus b minus x squared, the whole quantity. So I'm going to use parentheses. I can see that a couple times here. And that's going to equal c squared. So we just want to make sure we choose the correct one. It's b minus x squared, the whole quantity, plus h squared. So now they're asking us down here, use the answer from part 2 to fill in the blanks. They want us to expand b minus x squared using FOIL. So they want us to use FOIL because they want to know what is b minus x. So if I look over here, b minus x squared is b minus x times b minus x. So I'm going to do first, inside, outside, last. So first is b squared. If I do inside, that means negative x times b. And then if I do outside, that's b times negative x. So that's why there's 2 bx, and they're negative. And then if I do last, that's negative x times negative x, so that's positive x squared. So now we're going to add the h squared back to it. Remember, we just expanded this guy. So we're going to say plus h squared. So here I have it here. We just want to fill this in. So they rearranged it a little bit. We have x squared first, then h squared. And then I can see another square here. Well, that's my b. And then I can see minus 2. So I'm going to fill that in with b and x. All right, so now that we've expanded that, we're going to kind of ask another question here. So use the answers from part 1 and part 3 to fill in the blanks. So we're going to use substitution because we want to go back to that original part 1 there and say, well, what did a squared equal? And if you remember from part 1, a squared equaled x times x squared plus h squared. So here it is. I kind of brought it down so you can see it. That was part 1. So instead of a squared, I'm going to replace a squared, or x squared plus h squared, with a squared. So this section here, I'm going to replace down here with a squared because it equals a squared. And then I'm just going to bring down the other pieces. I still have b squared, I still have 2 times bx. So now I'm going to use trigonometry to fill in the blanks. So which trigonomic function would be used if you're looking at angle C and side x, because that's what we have here. And they're telling us it's cosine, right? So we have the hypotenuse over the adjacent, because that's angle C and x. So I have adjacent and hypotenuse. And I would have cosine of C equals x over a. Well, they have x equals, which means solve for x. So I'm going to multiply by a on both sides. And that's why I have a times the cosine of c, and there's no a here because these a's canceled. So I just have x equals a times the cosine of c. All right, one more piece here. So using the answers from parts 4 and 5 to fill in the blanks. So we're going to use substitution again, because what does x equal? We already know what x equals here. We just did that in part 5. X equals a times the cosine of c. So I'm replacing, instead of x, I'm replacing it with a times the cosine of c here. A times the cosine of c. And b still came down. We still have a and b squared here. So now we can see we just created the law of cosines where we're starting with that side c. C squared equals a squared plus b squared minus 2 times ba times the cosine of c. This similar approach could be used to prove the other 2 equations as well, because remember we have 3 different equations. So yours may not look perfect to this one when you're doing it on Alex, but it should look pretty darn close. All right, so on this one we're going to do another type of proof, expressing the area of a triangle in terms of sine of one of its angles. So we're going to relate the area of a triangle back to the law of sines. So we're going to look at the formula for the area of a triangle, which is to kind of remember. So the formula for area of a triangle is A for area equals 1/2 times the base times the height. Remember, the base and the height have to be perpendicular to each other. So when I'm looking at a base and a height, I want to look for that perpendicular line. And usually it's a dotted line. A lot of the time it is. And it's perpendicular to another side here. That's the base. And the height is the dotted line. Now, if you were looking at just the right triangle, say like just this bigger kind of right triangle on the side here, the base and the height would actually be the sides or the legs of the triangle. But when you have an obtuse triangle or an acute triangle, any other type of triangle that's not a right triangle, you're going to draw a line from the vertex to the other side, and it needs to be perpendicular. That's how we decide base and height. All right, so just like I said a few times here, the base is perpendicular to the height. So find the length of the corresponding base. So I kind of already pointed this out. 19 is the base because this is our height. So the perpendicular line to that is 19. And now we want to find the measure of angle P, or they're telling us, sorry, the measure of angle P is 45.93 degrees. So fill in the blank to complete the sine ratio. So remember, sine is so, if we're thinking about SOHCAHTOA. So that's sine of an angle equals opposite over hypotenuse. So we need to go through and label this. So if I'm looking at angle P, opposite is H, and the hypotenuse, even though it's not showing you the 90 here, there's a 90 on that side. So this is the hypotenuse, which is 7. Oh, I went too far. For some reason, I don't have the word hypotenuse written here. But so we have H over 7 for the sine of 45.93 degrees. Because remember, that's the sine of angle P. They just told us that's what it equaled. So now we're going to fill in the blanks in the expression for the area of triangle PQR. So I have H, and I'm going to substitute H. So I think one of the steps that they want us to do here, because they're having us bring down this area formula, the area of triangle PQR is 1/2 something times the sine of 45.93 degrees. So we want to show the base, which we did on part 1, times the height. Which this is a little bit funny. I don't think, did I work this one out? So I didn't actually show you this on the slideshow here, and I should have. So what they're doing is they solved for H here. So solve for H and then substitute. So they multiplied by H on both sides. That's why they have 7 times the sine of 45.93 degrees. And instead of H here, instead of base times height, they did height is equal to 7 times the sine of 45.93 degrees. So they're just substituting in the pieces there. So now if we scooch this up, we have this kind of bigger area here. And we're going to write the area of triangle ABC here in terms of BC and A, capital A. And we're going to think of the triangle above. Remember C, this whole length was the base. And B, why is it going backwards? And B times the sine of A, angle A, that was our height. Right, that's how we did this. And I'm looking at angle A down here, that was angle P here. This whole side C, well, that was this whole side 19. I'm just kind of matching it up to what we just did to kind of make sense of that. We would have a height going through here with the dotted line, and we would replace that H, that height, with B times the sine of A, just like we did up here. Because it was side B, that's where 7 came from, was that bottom side, and on this one it's B. So we're just kind of replacing those same things. We're making that connection between the two triangles. Shh. Sorry, you can hear my dog whining in the background here. So we have 1/2 times C, which is the base, times B times the sine of A, because that's what we're replacing height with. So this is just kind of a way of relating the pieces of the triangle back to its area. And this would be very convenient if you didn't have all of the pieces. Say if you had just one angle and you had side C and side B, then you could go through and you could solve the area of this triangle because you do have base and height. You just have them in a slightly different way. All right. So now we're going to look at day 13 here. We're going to go on to vectors. So a vector, and I like this little guy from Despicable Me. So can anyone explain a vector? Me, an intellectual. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. So he's 100% correct. He gives the actual correct definition in the movie. So this is what a vector looks like. It's an arrow. And the magnitude is how long it is, the size of the arrow. And the direction tells us, exactly which direction it's going in. It's pointing in the direction it's going in. We have tail and we have the head of the vector. And they're going to call this the initial and the final, I think is what they call it. The initial and the final point. So the initial point is where we start. Final point is where we end. Or terminal point, I think is another way they name it on one of the other screens here. So when we're looking at at a vector, we look at it in component form sometimes. And component form looks like a coordinate, just like x, y, just like we've looked at before, although the parentheses are arrow-like, like this. So we have vector equals, instead of a like curved parenthesis, it's this arrow-ish looking parenthesis. So I think we call it an angle bracket. And we have A and B. So we have two numbers in there. And what this represents, it's the difference in the x and the difference in the y's. So A, whatever number they give us here, A, is actually x2 minus x1. And B, that second number, is y2 minus y1. So they're doing that calculation for us in component form. It's already the differences between x and y, which we use on a few different formulas. We use that when we're calculating slope, and we use that when we're calculating distance. So the magnitude is another way of saying distance or length. So we can use the distance formula, although we're gonna convert it a little bit so that we can use it with this component form of a vector. So here's our original distance formula. We have the distance between 2 points when we have x1, y1, and x2, y2 is as follows. So we have it right here. Distance equals x2 minus x1 squared plus y2 minus y1 squared. Well, remember, if we have a vector and we're given component form, that first number they give us in here is actually the difference between the x's. So I could say A and B, because the second number is the difference between the y's. They've already done this little bit of math for us. We still have to square them, though. That part hasn't been done for us. So vector or component form just gives us a little bit of the math kind of ahead of time, I guess. They're doing a little bit for us. So here's the distance formula converted for a vector. So now we're going to just plug it in. So I have A is -4 and B is -2. Again, all this is the difference in the x terms, difference in the y terms. It's just, they're just giving us those numbers. I don't necessarily know the actual coordinates of the initial point and the terminal point, or the beginning and the end. So I'm going to square. I have 16 and 4, because -4 squared is 16, -2 squared is 4, and then I add them together to get 20. It does want it in simplified radical form, so you want to make sure that you break this down and pull any squares you can out. 20 isn't a square, so I can't completely take the square root because it doesn't want me to have a decimal form there. But I know if I break this apart into 4 and 5, 4 times 5 is 20, 4 is a square. So the square root of 4 is 2, and then I would leave 5 there. So make sure if you pull out a square, you're actually taking the square root of it. So that's why I separated into 4 and 5. And I know I'm just doing that out loud, and I'm only showing you the 2 root 5. But just kind of the idea there. Make sure that you simplify that. All right, so we're going to keep moving here on vectors. So we have scalar multiplication of a vector, geometric approach. So this one, you definitely need to, go on to Alex to do this one. You can do this one on your paper just as notes, but it's a little easier to do this one on Alex because there are tools on Alex that will allow you to drag the vector to the specified magnitude, which is the length and direction. So given the vector shown below, construct the vector 1.8s having initial point P. Use the tools provided to move the scale and scale the given vector. So they're going to give you one. It's always 0.1 or 1.0. And as far as I've noticed, it's always positive like this. So you need to make sure that you're paying attention. If it's positive, you're going to keep going in the same direction, but we need to make this larger. We don't want 1.0, we want 1.8. If it was negative, which I think we'll see on the one right after this one, we're going to switch directions because we want it to go in the other direction. We want it to be negative. So with this one, I want to make it longer. So it started, if you notice that kind of change, so it started here, and we can even see part of that arrow still on here, and now it's longer. So this is 1.8. I made it longer. Now when you're doing this on Alex, you literally will just click on the tools that are off to the side here and drag it until it matches the number they give you. The other thing you need to make sure is that it has an initial point P. So I need to click on my tools that allows me, the tool that allows me to drag the vector around. So it's usually the, not mouse tool, but the translation tool. I think it's like a 4-sided arrow, if I remember correctly. So when I click on that, I can drag this guy down so that it has the initial point where I want it to be. Because this one isn't quite done yet. If I click check right now, I won't get it right. I need to make sure I move it down so it's got the correct initial point. So this is just about moving vectors, kind of creating them. If we look at the next one here, so here we have a given vector shown, and we want to construct a vector negative 2.1a. So we can see the a here. The s and the a, those don't necessarily have anything to do with the direction. That's just part of the naming here. We also wanted to have an initial point P. And again, you would use your tools on there. So the first thing we want to do is make it the right length. So if we look at this one, I want to go the opposite direction. It was 1 positive. Well, I want to completely pull it down the other direction, so it's negative 2.1. So I completely switch directions. That's how you make it positive or negative. And then I need to make sure I change my tool and grab this guy and move it over so that it's in the right position. It's starting at P there. So this is all just about moving those vectors around. All right, the fourth one here is translation of a vector. So in translating a vector, we maintain its magnitude and direction. So we're not going to change its length. We're not going to change its direction. We're just moving it around. That's all we're doing. So a vector with an initial point, 6, 1, and terminal point, 3, negative 6, is translated so that its initial point is at the origin. Find its new terminal point. So first, let's go through and graph those 2 points. So here's my first point, 6, 1. So I went to the right 6 and up 1. And then I'm going to do the terminal point, that's the end. So here it is. I went over 3 and down 6. So here's my vector. I can see this pink arrow, right? That's my vector. We're going to translate that, move it, its initial point, so that its terminal point, I'll go back. We must move its initial point and terminal point the same distance and direction. So whatever we do to this initial point to get it to go to the origin, we have to do the exact same thing to the terminal point. Because remember, if we don't do the exact same thing, we're changing the size or the direction. We need to do exactly the same. We're translating. So if we go from 6, 1 to 0, 0, well, that means that I need to subtract 6. I have to move left 6 on the x coordinate, and then I also have to move down 1 on the y coordinate. So this is the same thing as saying I'm subtracting 6 and I'm subtracting 1. So we have this kind of format. This kind of gives us a key as to what we're doing. So we have minus 6 minus 1. So that got me to 0, 0. 6 minus 6 is 0. 1 minus 1 is 0. I have to do that exact same thing to the terminal point, to this point here. I need to move over 6 and go down 1. So I can look at the coordinates and do the same thing. I can go 3 minus 6 and negative 6 minus 1. So I would have negative 3, because 3 minus 6 is negative 3. Negative 6 minus 1 is negative 7. So I can see if I go over 6 and down 1, I do in fact land on negative 3 and negative 7. So I didn't change the arrow at all, or the vector. I just moved it over so that it basically has a new initial point. All right. So now we're going to look at vector addition and scalar multiplication, component form. So remember the components, that's just that kind of angular bracket. And then remember, this is just the difference in x's and the difference in y's, so that's why it's one number. So here are some basic vector operations. We have multiplication of a vector by a scalar. So a scalar means, what are we scaling it either up or down by? Suppose we have w equals wx and wy. So this is our x coordinate and our y coordinate, or our difference in x's and our difference in y's. And the vector and c is the scalar. So c is what we're multiplying by. The vector cw is defined below. So we have cw. Well, that just simply means I'm going to take whatever the x coordinate was and multiply by c. Whatever the y coordinate was and multiply by c. we're kind of just distributing that seed. It's a little bit like what we're doing. Don't go too far here. So that's multiplication. If we're doing addition or subtraction of a vector, then we're just going to look at it. Suppose we have u equals ux and uy, and v equals vx and vy. So we have two different vectors here. Goodness gracious, this mouse is too sensitive. And they're asking us first to say, what's the sum of the vectors? Well, that means that I have u plus v, and I did them in different colors just so we can see. So here's u, and I'd have ux and uy. Well, I want to add the x terms together and the y terms together. So I have ux and uy, and then I'm going to do the same thing with vx and vy. So I'm going to add the x's and I'm going to add the y's. Just like you kind of would with any other coordinates. Make sure you're combining the like terms or corresponding parts. I don't know necessarily if that would count in the same category as corresponding parts, but they are corresponding to each other in the respect that ux and vx, those are both the x terms, and uy and vy are the y terms. So same thing with subtraction. We're just going to subtract the x and the y. Oh, it's going to start circling 3m already. So u minus v, I do the same thing. ux minus vx, uy minus vy. So let's go ahead and look at that with some numbers here. So I have given the vectors m and n, and here are the numbers, and I'm just not reading them out loud. First, we're going to find 3m, and then we're going to find m minus n. So we're going to have two answers here. Okay, so let's do 3m first. So here's m, and we're multiplying by 3. 3 is my scalar. That's what I'm scaling it up by. So I'm going to take 3m, and I'm just going to multiply. If it's negative 2, I have negative 2 times 3. If it's 6, I have 6 times 3. So I'm just going to multiply, and that is my answer, negative 6 and 18. So now if I do m plus n, I'm going to do m plus n. So I did the different colors just so that you can kind of see the different parts here. But m plus n, so m is my red parts, and the n are the blue parts here. So I just did negative 2 plus negative 5, because negative 2 is the x portion, and negative y is the x portion. Negative 5, sorry, I think I said y. Negative 5 is the x portion. 6 and 7 are both the y portions or parts. Okay, again, they're the differences in x and the differences in y. So they're not truly a coordinate. That's not what it means. So we just simply subtract or add in a way, because it's negative 2 plus negative 5, so negative 7. 6 plus 7, we get 13. All right, we're going to try one more of these guys, and then I think we're going to do one more section today. So linear combination of vectors, component form. So we're basically doing the same thing we just did on the last one. We're just combining both operations. So we're going to multiply both vectors, and then we're going to add that together. So I did them kind of separately so that you can see. So first I did 5a. So we can see down here, 5a. And I'm going to multiply 3 and 5 by 5. So I can see the pink 5, that's my scalar. And the 3 and the 5 here, the red, well, that's what I started with the component form. So I'm just going to multiply, and I get 15 and 25. So that's 5a. I'm going to put that aside for a second, and I'm going to look at 3b. So I'm going to multiply each piece by 3. So 3b, I have the 3's here, my green 3, that's my scalar, and then I have 6 and negative 4. And that's what I got for my component form up here. So I'm just going to multiply, and I get 18 and negative 12. So now I can complete this addition piece. I can add these two together. So 5a plus 3b, well, that's going to equal 15 plus 18. Those are my x parts. And then 25 plus negative 12, those are the y parts of the component. So I get 33 and 13. So just had us combine a couple of skills there, a couple of the operations for vector for that last piece. All right, so I believe, if I remember correctly, I think this might be the last section for today. So we're going to look at dilating a segment and giving the coordinates of its endpoints. This is a little easier to do on Alex if you're actually on the program, because this sliding bar will help you do this. So a dilation is a figure that is enlarged or shrunk by a scale factor. So they're going to give us some kind of scale factor. If it's a scale factor smaller than 1, that means we're making it smaller because it's a fraction of what we started with. If it's a scale factor larger than 1, then it's going to get larger because it's more than 100%. That's kind of what 1 represents, is 100%, or the whole object. So to apply a scale factor or dilation, we just simply multiply by the factor of dilation, which is the scale factor. So for the figure below, do a dilation centered at the origin with a scale factor of 1/2. Then give the endpoints for both the original figure and the final figure. So here's the original figure, and we have this sliding bar at the bottom, and all I want to do is slide it to my scale factor. So I would slide it back to this half mark here. I put the original in the pieces here. So I have 4, 2. I can see 4 and then 2 and then 8 and then 8. Make sure you're paying attention to left, right, original, final figure. Make sure you're putting in the right spots, because you could have the right coordinate. You just typed it in the wrong spot, and Alex will mark you wrong because you're not kind of following the directions there. So now I've marked, I've written down where my original point was. I'm going to slide this over so that it's at 1/2 here. So here's my 1/2. This is half the size. If you notice, it got closer to the 0. So if we're scaling back, if we're getting smaller, it's going to get closer to the 0, and it's going to get smaller. If we're scaling up, if we have a scale factor bigger than 1, it's going to get larger, and it's going to get farther away from 0. So that's another thing to keep in mind there. So this one, we're just marking what are the coordinates. So now I have 2 and 1, and I have 4 and 4. And if you notice, 4 to 2 and 2 to 1, there's a pattern here. 4 divided by 2 is 2. 2 divided by 2 is 1. And if I do the same thing to 8, 8 divided by 8 is 4. 8 divided by 8 again is 4. So I can multiply or divide the coordinate by my scale factor. I'm technically multiplying by 1/2, which is the same idea as dividing by 2. So I can definitely do that to find my coordinates and make sure I'm in the right spots there. All right. So now we're going to look at the effect of dilation on a side length. So I apologize if this is a little small on your screen. I was trying to make it fit all on one screen here. So the scale factor for dilation is 2. So they told us that for the figure, do a dilation centered at the origin with a scale factor of 2. So they told us that. Then answer each part. So the first part they want to know is, what is the shortest length of the original figure? So we find the shortest side of the original figure is 1. We have this little guy here, this 1. And then they want to know what's the shortest side of the final figure. Well, if we're dilating by 2, it's going to get bigger. So I'm going to scooch this slide bar up to 2, and then I can see this is what I should find. It's just going to automatically, it's going to slide up there very nicely. It's not going to animate quite like that, but it does something very similar. But now I can see that the shorter side became 2 instead of 1. So what we can look at is that 1 times 2 is 2. So we get the following equation. The side length of the final figure is equal to 2 times the side length of the original figure. So we're just multiplying by that 2, which is kind of what we were looking at the end of that last one. I can multiply by the scale factor to find the coordinates. So true or false, a dilation with a positive scale factor greater than 1 gives a final figure larger than the original figure. So I already said this earlier. I'm just kind of talking about it. But we're going to look at these 2 notes pages here. So suppose the positive scale factor for dilation is less than 1. Then the sides of the final figure are smaller than the corresponding sides in the original figure. So they're smaller because it's less than 1, less than smaller. So the dilation gives a final figure that is smaller than the original figure. Now if we suppose that the positive scale factor for dilation is greater than 1, so now it's greater, so hopefully we can relate the idea that this the sides of the final figure are going to be greater than the corresponding sides in the original figure. So that means the dilation gives a final figure greater than or bigger than the original figure. So you just need to make sure you're paying attention to that idea. If it's smaller than 1, the final figure will be smaller. If it's larger than 1, the final figure is going to be larger. So this is true. This guy does fit in one of these two categories. True or false? The original figure and the final figure are similar. Well, unless we change the shape, they should be similar. All we're doing is making it larger, but all the sides should still be proportional when we dilate. Everything should dilate together proportionally. We're not just changing one side or a couple of sides. We're changing all 4 sides of this small little figure, and we're making all of them larger by the same factor. So yes, they are similar. All right, let's keep moving here. So these are other ones that are a little easier to do on Alex, but I can kind of show you the idea here. So they want you to use the sliding bar to determine if they are if they can be dilated. So determining if figures are related by dilation. Not by translation, rotation, or reflection, specifically dilation. So even if I can get this square on top of this square, which is actually what I want to do, the problem here is that they're exactly the same size. So I actually did this one and I copied it right over on top of here. So it's not a dilation because moving closer to 0 should have made the object smaller. I should be dilating down. But instead, it's exactly the same. So all I did was moved it. I translated this. So this is not a dilation. This guy, if I look at this one and then I make it larger, so I moved out, this is a dilation. The object became larger. It's moving out away from 0, so it's larger. And all sides are proportional. So if I look at this, it was 2 and 3. Now it became 1, 2, 3, 4, 5, 6. So that means that I multiplied by 3, because 2 times 3 is 6. So that means that this side better be 9, because 3 times 3 is 9. I have to make them proportional, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is proportional. All the sides were dilated. So, and now it's 6, 9, 6, 9. It was 2, 3, 2, 3. But now they're proportionally larger. All right. So, number 4, we have dilating a figure. So now they're giving us some kind of figure here. You do want to identify the points. That's going to be the easiest way to do this. So we're going to draw an image of the following figure after a dilation centered at the origin with a scale factor of 3/5. So 3/5 is smaller than 1. So our new final figure is going to be smaller than this original one. It's going to be closer to 0, closer in, and it's going to be smaller. So the first thing, number 1, identify your scale factor. And the second thing is we don't have a sliding bar on this one. There is no sliding bar at all. You're going to have to do the multiplication for this. So you want to identify the points. This one has 3 points. I have to go 1, 2, 3. It just depends on the shape they give you, how many points you're going to have. So I have 5, 10. I have 10, 5. And then I also have 10, 10. So I want to multiply each one of these coordinates. Each part needs to be multiplied by 3/5. So you can see I'm multiplying 5 times 3/5 and 10 times 3/5. It's not just one or the other. It's all parts are being multiplied. Remember when you're multiplying by a fraction? 5 divided by 5 cancels out. So this just simply becomes 3. 10 divided by 5 is 2. 2 times 3 is 6. So you can see it a little clearer hopefully here. I can cancel out the 5s and I'm just left with a 3. If I cancel out here, I can't fully cancel out the 10 because there's 2 5s in here. So it'd be 2 times 3. Or I could go through and do the multiplication if I don't like that canceling. 15 and 30 on the top, and then do the division. 15 divided by 5 is 3. 30 divided by 5 is 6. If I did the canceling, I would have still ended up with 3. And if I canceled here, I still would have ended up with 6. Kind of just depends on preferences there. So we're going to do the same thing on this next one. I just did exactly that. I don't need to remultiply. 10 times 3/5 is 6. I just did that. And 5 times 3/5, well, that was 3. They just switched spots because it was 5/10, now it's 10/5. And 10/10, well, same thing. 10 times 3/5, I already know what that is. That's 6. So I'm going to have 6 and 6. So here are my 3 points that I have. I graph the 3 points and then make sure you use your line tool to connect them. Because if you don't have the connection there, I don't know why it scooched forward. Again, this mouse is being a little sensitive. But if you don't connect them, I believe Alex will mark you wrong. You need to make sure that's exactly the same figure when you're done. All right. So now we're going to write a rule to describe dilation. So we have a dilation center to the origin with a scale factor of 3 is applied to triangle ABC. So this kind of lighter gray one. And the resulting ABC, we call this ABC prime, because that's what the little tick marks kind of let us know. It's the final figure. So we have this larger, kind of darker gray figure. And it's 3 times the size of the smaller one. They told us that it's got a scale factor of 3. So the arrows below show the coordinates on the left are mapped to the coordinates on the right. Fill in the blanks to give the coordinates after the dilation. So we have A, so this guy is going to be mapped to A prime. So we just need to say, what is A prime? So that's 3, -3, and +12. So we get -3 and +12. And then we have B and B, so B to B prime. So B prime is 9 and 6, and then C and C. So C is -9 and -3. So here we have the original and we have the final. And what they want us to do is make that connection between the multiplication that's happening there. So if I look at the original to the final, if I multiply everything by the scale factor, I will in fact get the correct coordinates. -3 times 3 is -3. 4 times 3, not -3, is 12. If I go to B, 3 times 3 is 9. 3 times 2 is 6. -3 times 3 is -9. -1 times 3 is -3. So they just want me to pick the rule that shows I'm multiplying x and y by 3. All the pieces there are being multiplied by 3. We're not changing any position, so we don't want y then x. That has to do with rotations and reflections. So we want to make sure that it's x then y, and both are being multiplied. So we want to make sure that we're choosing the piece here that's multiplying both. This one wouldn't work because it's only x being multiplied. Well, we multiplied y as well. And this one only shows y being multiplied and not x. Well, we definitely multiplied x. So we multiplied both x and y by 3. We did not divide one by 3 and multiply the other by 3. We did not divide both by 3. That would be a scale of 1/3. That would mean that the figure would have been smaller. We would have had a tiny little triangle inside of here instead of a larger triangle. So just make sure you're paying attention to, the scale factor. If it's a fraction, smaller. If it's a whole number larger than 1, well, it can have a fraction on it as well, but if it's larger than 1, it's going to be a larger figure. It's going to get bigger. So I believe that is it. That is all we have for today. I know that's definitely a little bit longer. I took the whole hour and a half there that we would have done in class, and we didn't even do any of the homework problems. So go through, if you need to go back and look at any of these pieces, definitely, you can rewind and go back and look. I also have these homework problems done on other videos too by day. So it's kind of limited a little bit more by day on Google Classroom already. And it's the QR codes on your notes pages at the top of the first page of each day for the notes pages. So I hope that helped, and I will send out the recording for next week as well, because I will not be in the office for the entire week next week. All right, well, thank you, and have a good couple of weeks here.